Hi, I'm Andy and this is question 8 on the OCR Mechanics 2 paper from January 2013. For more questions on this paper, click the eye in the top right corner. In question 8 we've got a conical shell of radius 6 metres and height 8 metres. And a particle of mass 0.4 kilograms is in contact with the rough inner surface of the shell. The particle is 4 metres above the level of V, so it's just here. The particle and the shell rotate with the same constant angular speed and the coefficient of friction between the particle and the shell is mu. In part 1 we're told the frictional force on the particle is F and the normal force on the shell is R, and we're given that the speed of the particle is 4.5 meters per second, which is the smallest possible speed of the particle for it not to slip. And in A, by resolving vertically, we need to show that 4F plus 3R is 19.6. So for a lot of this problem, I'm going to be working with a right angled triangle that goes up here, across the top, and then vertically down. And in this triangle, we know the height of the triangle is 8, and we know the base of the triangle is 6, and so if we label our angle down here as alpha, we can find out sine alpha and cos alpha. So just working with my triangle, I know that if this side is 6 and this side is 8, I can use Pythagoras and find out this side is 10 meters. And that means I can then work out the value of sine alpha and cos alpha. So sine alpha will be opposite over hypotenuse, 6 over 10 or 3/5, and cos alpha will be 8 over 10, which is 4/5. No need to actually work out the angle at any point in this problem, we can just directly use the values of sine alpha and cos alpha. Now let's think about the forces that are acting on this particle. We've got a normal contact force, which is perpendicular to the surface, and the particle is on the point of slipping back downwards, so the frictional force is having to work in this direction, and we've got a weight force acting downwards. So in part 8 we need to resolve forces vertically, but we're going to need to know some of the angles in here before we do that. So we'll label our alpha on the diagram, and we're going to figure out on this part up here which other angles are also alpha. So if I use alternate angles, going down here, across here and down here, I know that this angle will also be alpha, and as we've got a right angle here, means this angle will not be alpha, it will be 90 minus alpha, and as we've got another right angle here, it means this angle will be alpha as well. Another right angle here means that this angle will not be alpha, and then another right angle between the normal contact force and the friction means that this angle will be alpha. So I've identified various angles that will be alpha to help me when I'm resolving forces. So if I now resolve in a vertical direction, the component of the normal contact force vertically upwards will be R sine alpha. The component of the frictional force includes the angle, so that will be R cos alpha, both in the same direction, so both positive. And then vertically down, we've just got the weight, 0.4 g. And as the particle is vertically not moving, we can say that that is equal to 0. Substituting in values for sine alpha and cos alpha, we get 3/5 of R plus 4/5 of F, and I'm just going to move the 0.4 g over to the other side, so that becomes positive. All we have to do now is multiply both sides by 5, that gives us 3R plus 4F, and 0.4 g times 5 gives us 19.6 as required. In part B it says by finding another equation connecting F and R, find the values of F and R and show that mu is 0.336, correct to 3 significant figures. So we get our second equation by resolving in a horizontal direction. We'll take to the left to be positive. So we've got R cos alpha, the friction is in the opposite direction and it doesn't include the angle, so that's minus F sine alpha. The weight doesn't have a component in the horizontal direction, so we ignore that. And on the right hand side we have ma, which for angular velocity is mv squared over r. So the mass is 0.4, v squared becomes 4.5 squared, and to get the radius we use the fact that it's 6 meters at the top here, and this 4 meters is half of the 8 meters, so we're halfway up from the bottom, which means the radius across here where the particle is at will be 3 meters. If we sub our values in for cos alpha and sine alpha, we end up with 4/5 R minus 3/5 F equals 2.7. Multiplying through by 5 again gives us 4R minus 3f equals 13.5. So we have two equations here. I'll label them 1 and 2. And we can solve these simultaneously. Feel free to use your chosen method. Elimination is probably easier for these. I'm just going to do it directly in my calculator. So we get r equals 4.512. And we get f equals 1.516. And that means if we want to find mu, we use f equals mu r, so we end up doing f divided by r, so we get 1.516 divided by 4.512, which gives us 0.336 if we round to 3 significant figures. In part 2, we need to find the largest possible angular speed of the shell for which the particle does not slip. So remember, in our original diagram up here, we were thinking about when it was at the smallest possible speed without it slipping. And that meant this frictional force here was acting upwards to stop the particle going down. In the new situation, the friction is acting downwards to prevent the particle from going upwards. That's the only real change we've got to the situation. So because F is parallel to this surface, the value of R and things like that will be unchanged. So we have some very similar equations to what we had before. If I resolve in the vertical direction, I get R sine alpha minus F cos alpha minus 0.4g. So that gives me 3/5 R minus 4/5 F equals 0.4g. But the difference this time is that I can now calculate F, because the normal contact force hasn't changed in this situation. That only represents the properties of the two surfaces. So I can now calculate F, which means the only unknown I have is R. So we end up with 3/5 of R minus 4/5 multiplied by mu R. So 0.336, which we'll use the exact value for, and then R, and that equals 0.4g. Let's tidy up by multiplying by 5. And then here we can just factorise the R out, so we get 3 minus 4 times 0.336. And then we can just divide through by this bracket, which we'll do on the calculator. So as I might need this value more than once, I'm just going to store this value as A to use later. So I get 19.6 divided by 3 minus 4 times the value I've just stored, which gives me 11.8 newtons to 3 significant figures. Now I'll resolve horizontally. I've got R cos alpha plus F sine alpha. That's different to last time. And instead of mv squared r this time, I'm going to use the other version with angular velocity, which is mr omega squared. So 0.4 times 3 times omega squared. So this gives me 4/5 times 11.8. Again, we'll use the exact value. Plus, remember F is mu r, so we get sine alpha, which is 3/5 times 0.336 times 11.8. 0.4 times 3 is 1.2, so that gives me 1.2 omega squared. All I've got to do now is work this out on my calculator, divide through by 1.2 and square root. Before I do that, remember this is the value of R. I'm just going to store that as B, so I can use that in my calculator several times. So now I get 4/5 times B plus 3/5 times A times B. We divide all of that by 1.2, and then I'm going to square root the answer. And if I do that, I get 3.14 to 3 significant figures. And that's the end of question 8.